Okay, so this is problem 10. For problem 10, we have a Thevenin equivalent impedance, or just to calculate the equivalent impedance for this circuit, so seen from the node P. Okay, so in this case, I would just solve part C, because that's the most complicated one. You see that the other ones are just like simplified versions of that. But in order to calculate the equivalent impedance, or the Thevenin impedance seen from this node P, we first have to convert all the capacitance and inductances that we have here to basically a reactance, or a capacitive reactance, or like a capacitive reactance or inductive reactance. And for do that, we have to know the frequency. So in this case, the problem says that the frequency is 1 megahertz, right? And we also have to know how to convert the capacitance to reactance, or the inductances to reactances. So one thing is that we know that the capacitive reactance, right, is equals to 1 over j omega c, and the inductive reactance XL is equals to j omega L, right? And we remember that omega is equals to 2 pi f, right? And in our case, because we have 1 megahertz, that's going to be 2 pi mega radians per second, okay? So this corresponds in our case to 2 pi mega radians per second, okay? Now let's you see that in the circuit C, we have 1 microfarad for the capacitors and 1 microhenry for the inductors. So this leads to XC equals to 1 over J, because it's micro, it's 10 to the minus 6, right? It basically cancels with the 10 to the 6 of the mega radians per second. So it just becomes 1 over j 2 pi, and XL becomes j 2 pi mega radians per second times 1 micro Henry becomes j 2 pi. Okay, so that's the reactances that we have in the circuit. Okay, now to calculate the equivalent resistance seen from this terminal here, right? We just have to first, we can calculate this series here and simplify the circuit. We can calculate this parallel here. We can calculate this parallel here, right? Those three, they are all in parallel, right? So first, let's start with so I will call, let me just erase this part here. So I will put like some conditions here. So this is going to be our first, and I'll call it ZEQ1. Okay, so ZEQ1, so this is ZEQ1. So this is ZEQ1. Is the parallel between 1 ohm and 1 ohm, right? So which is the same as 1 times 1 divided by 1 plus 1. That's equals to 0.5 ohms. Now this ZQ1 is in parallel with XC, right? This 1 microfarad, which corresponds to this 1 over J2 pi. So let's call that ZQ2. So let's take this one here and parallel with this. And this is ZEQ2. So for ZEQ2, we have 0.5 times 1 over J2 pi divided by 0.5 plus 1 over J2 pi, right? And this is the same, so let me put it here. This is the same as 0.046 minus J 0.1445 ohms, right? Now, because we have ZQ here, this is the same Now we proceed with this series of ZQ2 with 1 ohm plus the inductive reactance J2 pi, right? So this is going to be our ZEQ3. So ZEQ3 is equals to ZEQ2 plus 1 ohm plus J2 pi, which is the same as 1.046, right? Plus J. So let me just here plus J. So it's going to be 2 pi minus 0.1445, which is the same as plus J 6.1386 ohms, right? And now this ZQ3 here is actually in parallel with, let me see, first in parallel with this capacitance here. That's our ZQ4, right? So ZQ4 is equals to ZEQ3 times the capacitive reactance 1 over J2 pi divided by ZEQ3 plus 1 over J2 pi, right? So this is the same as 0.00719 minus J 0.1632 ohms. And the final part is this ZQ in parallel with just this 1K. So this is our ZQ5, or I can call it just ZQ, right? So because that's the equivalent resistance or the Thevenin resistance, right? Which is the same as ZQ4, right? Times 1 divided by 1 plus ZQ4. And that's equals to 0.02662 minus J 0.1588 ohms, right? So that's the final answer, okay? So if you want, you can redraw the circuit for each one of the steps, but it's a pretty straightforward circuit, right? And I'm just doing like each one of the resistance one at a time, but you could also like build an entire equation there, and then you can calculate, okay? And for the other circuit, it's just the same approach. So for the first circuit, we calculate this parallel, then we calculate this series here, and then we end up calculating a parallel here. For the second one, we start with this parallel here, then we calculate another parallel here, another series here, and then another parallel all the way here. Or you could do like first one parallel with this one here, and then another one with that one, okay? Or even if you want to simplify even more this circuit, you know that basically reactances or inductances in series, you add them as if you had resistors, and for capacitors in parallel you also add them. So this one here, it becomes 2 microhenry. This one here, it becomes 2 microfarad, and this one here becomes 2 microfarads. Okay, so you just have to calculate new reactances, and then you just have you basically simplify the amount uh, of parallels and series that you have to calculate. Okay, so that's it for this